Greetings to everyone present at the 2025 conference. This is an important presentation that concerns detection of brain abnormalities in high-risk employees for early screening and enhanced workplace safety. The title of this presentation is Illuminating Abnormal Brain Lesions, an Explainable AI Approach to Automated Detection. The identification of brain abnormalities presents a significant challenge for clinicians or surgeons who wish to achieve precise identification of structural abnormalities and neurological functions by differentiating brain areas essential for language, movement, and cognition. Employees in high-risk environments, for example, laboratories with chronic exposure to high radiation, industrial workers exposed to neurotoxic substances such as heavy metals, athletes in contact sports with a high risk of head trauma leading to concussions, often face the risk of brain abnormalities that lead to movement and cognitive deficits. Work-related brain abnormalities often require early detection via advanced imaging techniques such as the magnetic resonance imaging, which is a non-invasive tool for diagnosing neurological conditions. Deep learning model integrated with explainable AI techniques can automate the detection of subtle brain lesions in MRI scans and provide transparent insights into the model's decision-making process. Therefore, our aim in this study is to develop a model that effectively detects brain lesion by combining two-dimension convolutional neural network, 2D CNN, and explainable AI using visual explanation like class activation maps, specifically reciproCAM. We highlight the significance of using AI-based MRI lesion detection system to ensure precise identification of abnormal brain scan for enhanced workplace safety and employee well-being through early diagnosis of neurological conditions. In this study, we utilized a data set comprising 9,000 brain MRI images sourced from AI Hub, with contributions from Seoul National University Hospital and the Catholic University Hospital in South Korea. This dataset, designed to ensure privacy, consisted of 4,500 normal and 4,500 abnormal images. The pre-processing stage included a focus on brain region and elimination of background noise. First, images were converted to grayscale, followed by smoothing using Gaussian blur. Thresholding was applied to generate binary images, ensuring the visibility of brain contours. Morphological operations such as erosion and dilation were used to clean up small artifacts. To isolate brain regions, contour detection was applied, selecting the largest contour for cropping. The resulting image, which focused on the brain, was then resized to 224 by 224 pixels for standardization. Finally, pixel values were normalized for efficient model training. We developed a customized 2D CNN architecture specifically designed for classifying brain abnormalities from MRI images. The architecture included 6 convolutional layers with progressively increasing filters, starting from 32 to 512, designed to capture both low-level and high-level features of MRI scans. Each convolutional layer is followed by max pooling and batch normalization to optimize feature extraction and ensure stable learning. Training was performed over 100 epochs with a batch size of 64 using advanced regularization technique and optimized strategies to improve performance and prevent overfitting. To enhance the interpretability of our model for clinical use, we integrated reciproCAM CAM, which is with the 2D CNN architecture. Reciprocal CAM generates saliency map with help to visualize the decision-making process of the model. The integration begins by multiplying the feature map of the target layer with a series of HW spatial masks. Each mask assigns a single value to a specific spatial position within the feature map. This generates a set of feature maps that are then processed through the remaining layers of the network. The predicted score for the target class are then used to populate the saliency map. The network is divided into two segments, F, the feature extraction, and G, the subsequent layers. The saliency map for a class is formulated using specific equation, where the confidence vector is calculated using the softmax function. In evaluating our model, the proposed two-dimensional CNN architecture demonstrated superior performance, achieving the highest accuracy of 95.9%. Efficient Net B3 followed closely with an accuracy of 93.1%. while ResNet 50 achieved 94.4%. The VGG16 model with an accuracy of 92.5% showed the lowest performance among the tested models. The 2D CNN also outperformed others across all evaluation metrics. It achieved an AUC of 0.98, a recall of 0.93, and a precision of 0.98. The F1 score was 0.95, highlighting its ability to balance sensitivity and specificity effectively. Efficient Net B3 and ResNet 50 delivered competitive results but slightly lagged behind. This figure presents the confusion matrix for 2D CNN, Efficient Net 3 B3, ResNet 50, and VGT16 models, respectively. The 2D CNN model outperformed the benchmark model in predicting both normal and abnormal class. Specifically, the 2D CNN model achieved the highest accuracy, correctly classifying 491 out of 500 instances for the normal class and 468 out of 500 instances for the abnormal class. This finding emphasized the robustness and reliability of the 2D CNN model in identifying brain abnormalities from MRI images. To enhance the interpretability of our proposed 2D CNN model for clinical application, we integrated reciprocal CAM to generate saliency map. These maps visualize the region of interest that the model considers critical for prediction. For example, in the case illustrated in this figure 6, the ground truth is labeled as an abnormal brain. The 2D CNN model correctly classified the image as abnormal with a class score of 0.9999 for the abnormal category and 0.0001 probability for the normal category. The saliency map revealed a specific area of brain MRI that influenced this decision. The color map ranging from red, high saliency, to blue, low saliency, demonstrate the features the model considered most relevant for classification. The highlighted area in red on the abnormal saliency map aligns closely with visible abnormalities in the MRI, reinforcing the reliability of the model's reasoning. In conclusion, the integration of 2D CNN models with reciprocal CAM demonstrates a significant advancement in early neurological diagnosis, particularly in employee health setting. This model's high accuracy paired with interpretability ensures effective and trustworthy AI-driven decision. By streamlining the diagnosis process, this approach not only enhances efficiency, but also will reduce costs. Thank you so much for listening and do enjoy the rest of the conference.